Hello, I'm Emmanuel. I'm a researcher at Leti in France. I'm going to present you our work on a recurrent neural network for always-on voice wake-up detection. Talking about voice wake-up system, so we have someone saying something like, "Hey Google," or "Pass me the salt." A start of speech is detected on the device, and a downstream machine learning decides whether it's useful speech sample. Our application is always-on speech recognition algorithm, and our objective is to reduce by a factor of 100 always-on power with smallest impact on recognition performances. Here's an example of input sample.
Wow.
We have here 10 dB traffic noise. Typically, the audio is transformed into some kind of spectrogram, and an algorithm will hopefully find the speech start. Here's the output of the SONVAD, which differentiates speech from noise based on their statistics. It can find the speech quite well in this stationary noise condition. In this example, we've used our features and used the classifier from Young. So it's a multi-layer perceptron with 3-frame context. So we can see it can find quite well also the speech. If we use this kind of example,
cat,
we can see that the SONVAD is completely confused. With the context MLP, we can see a few false accepts, which makes this system not usable in this type of environment. In our proposal, we use a recurrent neural network to capture the time dependencies as well as the frequency to have a better idea when the speech starts and differentiate it from other types of sounds. I'm going to describe our system. So all our results are obtained in simulation with a Python model. We're currently building our circuit. So a microphone is followed by a low noise amplifier, followed by an automatic gain control. So the goal is to maximize the SNR at all time in each band. So each band is composed of a bandpass filter, followed by continuously averaging of the absolute value. We sample that and feed it into a RNN alongside the gain code from the automatic gain control. So it shows a MGU, a minimal gated unit, which is a simplification from GRU. So it has only one gate. So we have about 1,000 parameters. Let's talk about our data and specification. So we use 5 phrases from the Google Speech Command dataset, 5 noises from the Musen dataset, ranging from very stationary to non-stationary. We follow a strict partition between training and test, 2 levels of SNR, 3 levels of speech level. We have clips between 3 and 10 seconds, and we have about 81 hours of speech. So the specification we concern with is not trigger rate, which impacts the performance of the whole system. And the false trigger rate will give us the amount of power saving in a specific noise environment. And so we want to operate in that green area. The SONVAD and the CMLP in pool condition not performing close to the specification we chose. As the MGU does, that's the floating point version. So you can see really big improvement on the 3% no trigger rate operating point. And when we quantize it to 4 bits, so features, weight, and activation, we can see we still operate within the performance specification. So we estimate the memory footprint to be 0.5 kilobyte and 45 nanowatt of power consumption on a high VT process. So to give a recap, we've seen that robustness to unseen non-stationary noise is really hard to achieve. We use gated recurrent neural network for capturing temporal information as well as frequency. And we achieve this in a very small memory footprint and power consumption. So thank you for your attention, and please check out the full paper for more details.
No online questions, but I would be actually interested in the power consumption. This estimation to 45 nanowatt, what does that include? I mean, is that just the
so this is this is just the classification. So for the overall circuit, like our target is 1 microwatt.
Okay. But you did that in you said you did a power Python modeling. So is that power modeling also done in Python, or how did you actually do the power
So
modeling?
for the classifier, we did a RTL version of it, and then digital synthesis. So, but it's actually on 0.9 volt. So we should get lower on the real circuit when lowering the VDD.
And for these filter banks, how many of those filter banks are you using?
16.
16 filter banks, okay.
Yeah.
So the analog filter banks, I mean, they're not of the RNN. So I mean, really the bandpass filters from in the analog domain.
Yes, 16 is more than enough for the voice wake-up task.
Okay, thank you.
Again, just a quick shout out to our sponsors. Bear with me for 1 minute. We have different categories. We have executive sponsors. First one being ARM. Then we have Qualcomm. We have Samsung. Platinum sponsors. Ada Compute. Lattice Semiconductor. Gold sponsors. BrainChip. Babel Labs. DSP Group. Edge Impulse. EMSA. Gray Matter Labs. Greenwaves. Hymax. Imagimob. Latent AI. Maxim Integrated. Quixo. Reality AI. SensiML. Silicon Labs. Sentient. Google TensorFlow. CMOS. And lastly, silver sponsors, Edge Cortex, Hotchi, and Synsets.